Hi, today we're going to talk about Bernoulli's principle. So, Bernoulli's principle basically just says this, that if the velocity of a fluid increases, then the pressure of the fluid decreases. That's basically it. Now, it's going to be a little bit more detailed, but let's just think about this. So, here I have a pipe that has a certain diameter and it moves into a narrower diameter section. Now, remember, the continuity equation tells us when this happens, the velocity has to increase in order for the flow rate to stay constant. So, we find is in this section here, if we put a pressure gauge here, we're going to find this pressure here. But if I put a pressure gauge here, because the velocity went up, I'm going to find that the pressure went down. And when I come over here and the velocity of the fluid slows back down, I'll find the pressure goes back up. So basically, if the velocity goes up, the pressure goes down. If the velocity goes down, the pressure goes up. Now, the most common illustration of this is an airplane wing. This gets discussed quite a bit, and it's one you should know. So basically, I have two air molecules here, A and B. They're just side by side. They're not moving. The air is still. An airplane is going to fly by, and so as it does, it's going to pass by A and B. Now, let's just say it takes 1 second for this to occur. So A and B are side by side. 1 second later, they're still side by side, having really not gone anywhere other than being separated by an airplane wing. Well, if we look at it from A and B's perspective, what we find is that A traveled a greater distance than B did, and it did it in the same amount of time. So what that tells me is this. A went a greater distance in the same amount of time, so it must have been traveling at a higher speed, and therefore high speed makes low pressure. On the bottom of the wing, B went a smaller distance in the same amount of time, which means it was traveling slower, and therefore the pressure was higher. And that pressure difference between the top and the bottom wing is what keeps the airplane up in the air. It has to have a certain speed difference between the top and the bottom to have enough pressure difference to lift in the air. I don't know about you, but when I look at an airplane before I get on it, I'm like, there's no way this thing can actually go in the air. But the reality is, when you have enough speed difference between the top and the bottom wing, you have enough pressure difference to lift the thing in the air. Now, Bernoulli's principle, to really understand it, you have to accept the fact that it's basically a statement of conservation of energy, which we've dealt with a lot this year. So, remember, basically what we say with conservation of mechanical energy is if I sum the kinetic and the potential energies, they don't change unless work is being done. So let's just say I have a system where there's no external work being done. There's no energy being lost from the systems. There's no friction with the walls or whatever, okay? So if I say k plus u in this section, it has to equal k plus u in this section. Otherwise, I have either increase or decrease its energy. So since this is going faster, the kinetic energy has to go up. That means that the potential energy has to go down. All right, that's the basic idea of Bernoulli's principle, is that the kinetic energy is due to the speed. Therefore, the pressure, which is a form of potential energy, is going to go down. Now, why is pressure a form of potential energy? Let's take a look at that one next. So here's, I think, the best way to wrap your head around this idea that gauge pressure represents potential energy. So here I imagine I have a container. It is open to the atmosphere. So the gauge, remember the gauge pressure is just how much above or below atmospheric pressure you are. Since I'm not at all above or below it, it's going to read 0. Now here's what I'm going to do. I'm going to pump air molecules into here. Now in order to do that, I have to apply a force across a distance, say with a piston, to push these molecules in here. And as I push them in, the gauge pressure is going to go up. I want to say from 0 to 2,000 kilopascals. And it took a lot of work to do that. So I added energy to the system by doing this work. Then I seal it off. Well, that energy can't go away. So that energy is still present in here. And the form that it takes is this gauge pressure. So this pressure is essentially a measure of the potential energy of this gas that it has because of the work done putting the gas into there. Now watch this. If I later open up this valve again, what's going to happen, as you well know, is that the air is going to come rushing out of here, gaining kinetic energy. But you can't create energy from nothing, right? So the total energy of the system isn't changing. So if I'm gaining kinetic energy, I must be losing potential energy. And as you are sure you're aware, the pressure is going to go down. Well, why is the pressure going down? Because this pressure represents the potential energy that's doing the work to push the molecules out and give them kinetic energy. So basically, the simplified version of Bernoulli's principle, where there's no change in hydrostatic pressure, there's no change in elevation of the fluid, can be written this way. So basically, I take the initial gauge pressure plus the initial kinetic energy. But notice, instead of saying mv squared, when dealing with fluids, it's kind of tricky. So we're going to talk in basically kinetic energy per unit volume and pressure energy per unit volume is how we're going to do this. So what I get is pressure is equal to 1/2 the density of the fluid times its velocity squared. And that's going to be true for the final conditions as well. So basically what I have is gauge pressure and kinetic energy, but these are both expressed in terms of per unit volume. So let's just try to make sure we understand what that means. It's not that crucial that you do for the AP test, but I want you to have an understanding of it so you're not just accepting it blindly. So here you go. So if I want to understand why kinetic energy would be represented that way, kinetic energy, remember, is 1/2 mv squared. Now I say, well, I want to do it in terms of per unit volume of fluid. Well, so I'm just going to divide both sides by V. So if I divide this side by V, well, what's mass divided by volume? Mass over volume is density. So what I find then is the kinetic energy per unit volume is equal to 1/2 the density times V squared. Pretty straightforward. Now we're going to do the same thing with pressure, but it's a little bit different. So remember, pressure is force per unit volume, right? F over A. I'm going to rearrange this equation in terms of force. So force is equal to pressure times area. Now I'm going to go over and look at my work equation, because remember, it's the work we did putting it into that container. So work is equal to force times distance. I'm going to take the F and replace it with this. So work is equal to pressure times area times distance. But wait, area times distance is volume. So I could say work is equal to pressure times volume. Again, you're not going to have to like recreate this on my test or the AP test, but let's just work your way through this. It's kind of cool. So therefore, pressure energy, the work done making that pressure go up, is equal basically to pressure times volume. But if I want to express it in terms of pressure energy per unit volume, like I'm expressing the kinetic energy per unit volume, I'm going to divide it by V. And look, V over V, I just get P. All right. Now, let's look at an example of this that illustrates it. So again, we'll go back to what I had, where I have a pipe that goes through a narrowing. Okay, so I have a gauge pressure of 200,000 pascals or 2 kilopascals or 200 kilopascals, and I have a speed of 4 meters per second. When it goes into here, its speed has to increase, so it goes up by a factor of 4. And I want to know what the new gauge pressure is. So I'm simply going to say P1, I'm just going to use, the Bernoulli's equation. So P1 plus the kinetic energy equals P2 plus the kinetic energy per unit volume. So I'm just going to substitute in 200,000 pascals. Remember the density, this is supposed to be with water. So is water flowing through here? Does it say? Yes, it says water. So water has a density of 1,000 kilograms per cubic meter. And I have to be in kilograms and cubic meters because I'm going to be talking about meters per second square, meters per second, okay? So it was traveling at 4, so I put 4 squared equals P2. Same thing here. And when I solve this, I'll get 80,000 PA. So I went from 200 to 80,000, which makes sense because as the velocity increased, the pressure had to go down. So basically, think of it this way: what provided the work to speed this up? It was the pressure energy. So the pressure energy here did the work speeding this up, so it has less pressure energy. Now, a classic example of this that you'll probably see on the AP test, it's a very, very common question to ask, is this. I have a large tank of water and I shoot a bullet into it and it punctures it at a certain depth and the water comes out. And a lot of times they're going to try to combine it with two-dimensional kinematics. I'll do the same thing, all right? And we'll ask you, where's this going to land? But the bottom line is I need to know, what is the velocity that it comes out of here? So right now we're just going to say, what is the velocity the liquid comes out? Uh, if it contains a liquid of unknown density, by the way, and the bullet hits the tank at the 4 meters below the surface. So let's just see how we would solve this. So I'm going to set up Bernoulli's equation. Again, I'm going to, in this case, I'm going to treat hydrostatic pressure as gauge pressure because that works here because this fluid is static. So if I was to simply take a pressure gauge and move it down here, the pressure would basically be measuring the hydrostatic pressure. So I'm going to use this. Now for P1, I'm going to basically use it as hydrostatic pressure. So I'm going to say, remember that's density times G times H plus at the initial conditions, the water is not moving. So the velocity, the kinetic energy is 0. Afterwards, when it comes out of here, there's no more hydrostatic pressure here. So we're going to say, well, the pressure here is 0. So therefore, it's going to be traveling at this V because of its kinetic energy. And when I go to solve it, it looks very familiar, doesn't it? It just turns back into, as it always does, root 2GH. It's really simple, okay? But the trick here is you have to understand that the gauge pressure in this case is due to the hydrostatic pressure because this fluid isn't moving and it's open to the surface here. Okay, now let's just move a little bit farther into this and let's say, okay, well, we could also have a change in height here. So the fluid could be gaining or losing gravitational potential energy, which is a form of energy we need to take into account. So I have pressure energy, I have kinetic energy, and I have gravitational potential energy per unit volume, which is the same thing as its hydrostatic pressure. So I'm just expanding the equation by putting this expression for gravitational potential energy on each side. Well, let's just see how this works out then. This is kind of a classic setup that you'll get, and you probably will have to solve one of these on your test. So basically, I have a pipe that has a radius of 0.5 meters. It's going to come uphill and it's going to come here. And It's now traveling. It goes from traveling at 2 meters per second to traveling at 4 meters per second. Uh, Actually, what I really need to know here is just that the height of the middle of this tank, of this pipe rather, is 0.5 meters. I don't really, because I'm told the velocities of it. I don't really have to use the continuity equation to do that, but I do need to know how much potential energy it has between here and here. And so if the middle of the pipe here is at zero point 0.5 and the top of the pipe here is at 0.25, well, then that lets me know that I have 2 meters of delta H. So anyway, so what I want to know is what was the gauge pressure initially if I end up with these, if it goes 2 meters in the air, is traveling, it goes from 2 to 4, and it ends up at 100 kilopascals. So I'm just going to use the expanded Bernoulli's equation, which is basically gauge pressure plus kinetic energy plus potential energy. And I'm just going to substitute in these values. It's water, so the density is 1,000 kilograms per cubic meter. The velocity here was 2. We're going to call this height here 0, so we're going to use this as our reference point for gravitational potential energy. And now when I come up here, I have a gauge pressure of 1,000 kilopascals, so 100,000 pascals. Remember, this has to be in pascals, not kilopascals. Again, the density is 1,000 kilograms per cubic meter. It's now traveling at 4, and it is 2 meters higher than it was here. And so when I solve this, I find 126,000 kilopascals, and that makes sense. It basically lost pressure moving up here, going uphill and going at a faster velocity. We're going to look at one last one here. Okay, so I have jet fuel that has a density of 0.8 grams per milliliter. Like, you got to be careful. I can't use grams per milliliter, but that's how we often express densities. It's flowing through a pipe with a diameter of 1 meter at a speed of 5 meters per second, and gauge pressure A reads 200,000 pascals. And I want to know, what is the pressure reading on B? What I do know is that the diameter of the pipe over here is 0.5 meters, so it has half the diameter. So how would I go about this? Well, the first thing is I have to use the continuity equation to figure out what the velocity is here, because I can't do Bernoulli's unless I know what the kinetic energy is. So what I'm going to do is I'm going to say, well, area 1 times velocity 1 equals area 2 times velocity 2. So the area here, well, I had to take the radius, that's 0.5 squared. So I'm going to say pi r squared times the velocity is equal to pi, in this case, r is 0.25 squared times this velocity. And when I solve this velocity, I get 20. And it makes sense because the area is going to be 4 times smaller here, and therefore the velocity should be 4 times bigger. Now, I'm going to go here and say, all right, let's just solve this. There's no change in gravitational potential. I'm not going uphill, so I don't have to worry about that. So I'm just going to say, I'm going to use the simplified version of Bernoulli's equation. I'm going to substitute in the values here. So the gauge pressure here I was told was 200,000. 0.8 grams per milliliter. Remember, if I multiply grams per milliliter by 1,000, I get kilograms per cubic meter. So that gives me 800. The velocity is 5, so 5 squared is going to equal P2 times, and I use 20 squared. And when I solve it, I get 50,000 PA. And so I see I went from 200,000 to 50,000, which is in line with what I'd expect. It's going faster, so it has less pressure. Okay, so it's really not that hard. It's just basically conservation of energy all over again. Thanks for watching, and we're done with fluids now.